Okay, here we are. Jeffrey Fox, data science curriculum. Not very good at circling here. Big data, open source software and projects course. And we're on lesson 2E in the data access patterns introduction to using HPC ABDS. That introduction is units 2D, 2E, 2F, and 2G. So this is the second unit in the summary of the HPC ABDS layers. And let's get going on that. Next slide. Okay, here we are. We're looking at the HPC ABDS stack. We're on to layers 7 through 13. As we'll see on the next slide, these cover several very important areas. So 7, 13. So that's interoperability, file systems, cluster resource management, data transport, all of file management, including SQL databases and the very popular now NoSQL technologies, the so-called new SQL technologies that merge those together, a bunch of important tools here to get good performance, and then finally a critical layer which captures the communication between different processes. You have your different stack members and they need to talk to each other. That's layer 13. So here we are. Let's get on with it. Thank you. Now we come to layer 7, which is interoperability. And we have two types of interoperabilities, what you might call libraries, which achieve interoperability by building into some software the different ways of doing things. The alternatively is actual standards, which insist people do things in the same way because they obey a certain standard, and then you do not need a program to do this for you. We have libvirt, which provides interfaces at the hypervisor level, and libcloud and jclouds at the cloud provider level, where they're doing it as programmatically. Tosca is a pretty interesting standard. It comes from OASIS, a famous standards body, and it actually is sort of specifying the types of capability as a standard, which is done by systems like OpenStack, Heat, or Juju. Aki is a cloud standard which specifies how to do computing, like Amazon EC2. CDMI is a storage like Amazon S3, and WER is a way of doing services in a cloud-neutral fashion. Saga and Genesis are well-known systems from the HPC community. They provide standards for distributed computing and both the computing and the storage aspects of grid computing. Layer 8 is file systems, and everybody actually uses a file system because you can almost always have disks somewhere, and those disks have to get used, and by definition what goes on top of a disk is a file system. We can have different types of file systems with various performance and functionality trade-offs, but it's by definition file systems. So you always use a file system. However, you may not always expose that to the user. So actually, if you look at most commercial systems, they don't expose the file system to the user. Rather, they expose an object store or something like that to the user. That's what Amazon does with S3, for example, and OpenStack does with Swift. And most science applications and research applications are built possibly for historical reason around files. You know, there's a famous systems like NFS, Network File System, and other related systems where we have things like in this category, Lustre is an example of a wide area file system allowing multiple computers to share a set of files. So it's sort of interesting to read what happened at Facebook. They originally used NFS actually to store images, but they found that too slow, and they built their system called Haystack, which is effectively a customized object store. And then they built on top of Haystack F4, which is actually has ingenious definitions of images. They're either cold and they hardly ever access warm, which are sometimes accessed hot, which means really exciting. Lots of people want to see this nifty image. And depending on the the temperature of an image, you can actually have different strategies about how it's cached and how you deal with it to get the best performance. There's this well-known principle, or you should always bring computing to the data, not the data to the computing, and that is realized by HDFS, the Hadoop file system, which builds on the Google file system. This underlies Apache Hadoop and all sorts of tools of that ecosystem and related ecosystems. OpenStack has Cinder, which implements the block store used in the Amazon Elastic Block Storage and the Azure files and Google Persistent Storage. These are analogous to disks directly accessed on a computer in a non-cloud environment. And we've already mentioned Swift and S3 and Azure Blobs and Google Cloud Storage, which implement back-end object stores. Fuse is an interesting technology. It's a user-level file system which is used by Gluster, which is one of the HPC, I should say, cluster community file system. Ceph is interesting. It actually allows itself to look like an object store, a block store, or a file store. GPFS is a famous parallel file system supporting parallel computing in a very efficient fashion with technologies like MPIO, which is the dominant HPC way of getting data in with very high performance and minimal latency into a running parallel computer. GFFS is the federated file system used in Exceed, and it comes from Genesis 2, which was defined in the last layer, and it allows you a uniform view of a set of distributed file systems on lots of different computers and makes them look as though they were sitting on your local client machine. So now we come to cluster resource management, layer 9, and there are many entries here, of which from HPC community, the most well-known will be things like Moab, Talk, Go Together, OpenPBS, and Sun Grid Engine, now called SGE, because Sun was taken over by Oracle. These are all similar, well-known HPC scheduling systems and resource management systems. HT-Conda is possibly the most prevalently used of these, and its game was a dominant grid computing capability. Then we have on top in the HPC world, we have Globus and pilot jobs. These allow you to solve at least try to address the meta-scheduling problem, which is you have lots of computers, you want to run your job on that set of many computers, but they each have their own schedules, and so that requires appropriate abstractions and technology to make it work correctly. Coming back to actually the first paragraph, which I sort of skipped over in my enthusiasm for HPC, we have actually an important recent development. Yarn has become very important in the refactoring of Hadoop. They broke out the schedule. That's because people like me used to write lots of papers saying how you could improve it. Mesos is a similar effort from the famous UC Berkeley effort in this area. Helix comes from LinkedIn. Notice this is an example where Apache has many entries in this field, Helix, Mesos, and Yarn. Llama comes from Cloudera, and it is essentially built to work with Yarn and allow reuse of processes. It's well known that Hadoop takes a long time to get started. So if you can reuse processes, you can cut down latency and get better performance. Well, if we were Google or Facebook, we will think what most of people like me do is trivial, and so we would need to address job scheduling or management at a far larger scale than anything I do, some infinite scale, and they have Omega and Corona respectively, which are proprietary resource managers, if you like, much larger versions of Yarn and Mesos. Customized to run huge collections of jobs. Celery is a nifty suite system which sort of captures the master worker model using RabbitMQ to do publish subscribe, so that that provides an interface similar to say what Azure does with the worker role and Azure queues. So queuing for Azure queues being replaced by RabbitMQ in Celery. Layer 10, where we have data transport. And there's not so many entries here, so it's actually a little surprising. We have the most famous or infamous is BitTorrent. It used to be around a third of the internet traffic 10 years ago. It's now a few percent, 3 to 4%, but still non-trivial, of course, given the many candidates to use the internet. We have core technologies like HTTP allows you to send data back and forth, uploading and downloading. FTP is, of course, used a lot. And the secure versions of that, of course. SHH is a similar type of secure technology for linking computers together and sending information back and forth. Grid FTP was one of the most important contributions to the grid computing activity, and that's now captured in a very elegant solution called Globus Online. And there's not so much from Apache at this layer. There's Flume and Scoop, which correspond respectively to transporting logs and transporting distributed data for Hadoop. So that's it. I would think there should be more entries at this level because this is critical. You have to move data about. You can't always assume it lives in one cloud. And maybe that because actually in today's world, most things just go to a cloud and just sit there, you don't see so much work in this area. But certainly in research areas, that's not true because you have to gather data from all over the world. Data is distributed. You need so-called data grids, and how you do transport is very important. And I say Globus Online for the research community is, I would say, the best available solution. Layer 11 has these three levels. 11A is file management, and it has three types of entries here. We have iRods, which is comes from University of North Carolina. Reagan Moore, who used to be at San Diego Supercomputer Center, but moved to North Carolina and took what was called the Storage Research Broker SRB and developed it into iRods, which is a very sophisticated file management system. It manages both files and the metadata associated to files. And there is no such system in Apache. I was really quite surprised. Most of the times Apache had many entries addressing what HPC community had done. In this area, they don't have anything, presumably because in the Apache applications, they're going to use object stores, not files. And so the equivalent of iRods is hidden under the hood of an object store. We also have here, the rest of the entries here are actually formats. NetCDF, CDF, and HDF are famous array-oriented formats optimized for scientific data. OpenDAP is a format optimized for the earth science community. FITS is a format optimized for astronomy, a very old and well-established format. The last three are reasonably interesting. RC files, awk, come from Hive. They're their formats. How Hive stores its data on disk to get very good performance, and that's actually an issue of sort of actually what MPI.io does. Namely, you want to store data on disks in such a way that you get good performance, and that means you have to decompose over rows and columns, and that's why RC is present in the name, because these are row-column decompositions. Parquet comes from Google, yet another brilliant Google paper, this one on a system called Dremel, and it underlies the column storage in many systems, which we'll come to later at layers 14A and 15A. So that's 11A. Now we have 11B. It's the densest of all these slides, just because there are lots of entries in this layer. This is the NoSQL layer. It's remarkable how many entries there are here, including many from Apache and other open source sources. And there's nothing at 11A except iRods from HPC, whereas these systems here are not coming from HPC. So we have 6 types of NoSQL system, what we call tools, which are building blocks. We have key value stores, document-based stores, column-based stores, graph-based stores, and a special case of graph-based stores, triple stores. And here we have a list of what we have. We have Lucene, Solar, and Salandra, which are aimed at information retrieval under tools. Key value stores are called REACT, is possibly the best known. It uses Solar for search and is based on the ideas in Amazon Dynamo. It's not a Google invention this time. Voldemort comes from LinkedIn. Berkeley DB comes from Oracle. Azure Table and Amazon Dynamo and Google Data Store come from the public clouds in this NoSQL key value area. Document-based stores, sometimes very good to go. You just have documents, and inside each document you have tagged elements. And MongoDB is the most famous of these, an open source product, very well supported. Espresso comes from LinkedIn, and it uses the Helix Layer 9 resource manager. CouchDB is from Apache, is very well known. It has a breakaway Couchbase, which adds caching and memcache features. Then along came a company, Cloudant, which actually took Couchbase and extended it and then actually made it sort of proprietary, enhanced it, and then they sold that. Cloudant was just purchased by IBM, who put it into their cloud offering. Column-based stores, that's sort of the original NoSQL. There was HBase, Cassandra, and Accumulo are all in this area. And then we have various important variants of it. RYA was a triple store built on Accumulo. Squirrel is built on Accumulo to do security. And here's something pretty interesting. Megastore and Spanner, they extend the big table idea to provide more robust synchronization in the distributed fashion or coordination so that you can produce ACID-style SQL systems. And we'll see that in level 11C. Okay, so Neo4j is a graph database that claims to be the most popular. I must admit, it's not the one I hear most about. Eureka is often very popular in the fields I work on, partly because it's supported by Cray, because it likes to do shared memory for graph-based algorithms. There's some people in the graph community who like shared memory and some that like a distributed memory. So there's an important W3 standard called SQL. Called Sparkle, not SQL, sorry. The analogy for graphs is Sparkle, where SQL is for traditional data, and Sparkle is specially aimed at triple stars. And Allegro Graph is a commercial system written in Lisp and integrated with MongoDB and Solar. Tao from Facebook, which Tao is an abbreviation for the associations and objects. And we know Facebook with all this linked list of people from who's friends of who and things like that. So they have lots of interesting graph problems, and Tao is a system they built to support that, which is obviously designed to scale to a huge size. TitanDB at least looks interesting from its description. It integrates with all sorts of technologies, Cassandra, HBase, Berkeley DB, and a nifty thing called, at least in terms of its name, called Tinkerpop, which is a graph processing stack. It's at layer 16. It also uses Hadoop and Elasticsearch and Solar. All right, finally we have here is triple stars, and they're a special type of graph. When you do RDF, you have a resource attribute and attribute value gives you a triple, and you just have a list of resources. The attribute, like the resource might be me, I'm a resource, and I have attributes like name and where I live and what I do, and those attributes have values like Jeffrey and teach boring courses is what I do, and so on. And so RDF is very famous for supporting this type of storage, And then when you get all these triples, you have to search them efficiently. And they also link to each other in a natural fashion. And Apache Gina and another open source product, which is not Apache, called Sesame, supports such triple stores. 11C. Okay, we're almost ending this lesson. So this is SQL and NewSQL. So what is NewSQL? NewSQL is basically a system which uses Hadoop style or MapReduce style technology, cloud, brilliant ideas, but offers to the user SQL semantics, including the robustness and the so-called ACID properties of clean, predictable results. And they do this by effectively noting that Hadoop and MapReduce give you very good parallel computing capability, better than those used in traditional databases. And with that parallel computing, you can, if you put in enough constraints, which actually slows performance, you can get the traditional quality of a SQL database. So in this category, we don't pretend to list all the many relational databases. We just list three major ones: Oracle, IBM, and Microsoft. Then we have the low-end ones. I don't mean they're negative. These are lightweight ones that tend to be used by many users. Apache Darby's the lightest, and SQLite are the two lightest. Then we have the famous MySQL system and Postgres, which are all open source. There are various ways of parallelizing these systems. Galera cluster is one particular approach to that. An interesting new development is the development of array-based data source. So SciDB and Rasterman support arrays with great efficiency in a traditional database environment. If you go to a public cloud, you'll be able to buy access to such databases, and that's Google Cloud SQL, Azure SQL, and Amazon RDS. Relational data systems. N1QL is a nifty concept, and which illustrates this new SQL trend, and it basically adds SQL queries to the NoSQL system we mentioned in 11B called Couchbase. Google F1 builds on Spanner, which we mentioned in the last section, layer 11B, and it delivers very robust SQL technology on this scalable framework. DashDB is a similar concept. It offers warehouse capabilities similar to Amazon Redshift, which is in a later layer, and it's built on top of this cloud and software, which we mentioned in layer 11B. BlinkDB is sort of out in left field. It's a research database from Berkeley, which explores sampling to speed up queries on large data sets. Okay, this is the last slide of this lesson, layer 12. Not so much here. This has actually multiple types of things. In-memory databases and caches, as I mentioned, this is critically important to get good performance. All these famous internet systems use this or this type of technology. Google App Engine is well known to use Memcached as its caching technology. Redis is an in-memory key value store, and Hazelcast, EHCache, and InfiniSpan are all supporting this caching so that they minimize the amount of time you have to spend accessing disk. UMAR and Tika are extraction tools, and UMAR is famous for being used in the by IBM Watson and IBM Watson won Jeopardy. And the last set of so-called object relational mappings, and these are either mappings inside memory or more sort of directly. They map from sort of Java objects living in memory to relational databases or other forms of persistent store on disks. So that's the end of this lesson. And the next lesson we'll go through the remaining layers and then do an overall summary of the whole stack. Thank you. This is Jeffrey Fox, the instructor for this big data software class, and thank you very much for sticking with it. Thank you. All right, so layer 13. And this is on communication. So we're always doing parallel computing because that's how we get scaling and that's how we can process mammoth amounts of data. We've got to chop that data up and process different bits on different machines. So communication between processes is very important. And we have a whole set of capabilities here summarized in a couple of slides. And they cover a variety of different capabilities. There's MPI. This is the world's fastest way of sending information between two processes. And it streams that data and tries to minimize, not it suddenly doesn't write it to disk, but nor does it write it to memory where possible. It just tries to date the data directly from running program number 1 to running program number 2. And because of its attention to performance, the latencies can be as low as a microsecond, 10 to the minus 6 seconds for the time it takes to get between processes. Now that contrasts with disk access, which is say what a Hadoop would do, if we read and write from disk. You're not going to do anything with a disk without incurring at least 10 milliseconds. So that's 10,000 times as long. And if you double it to read and write, you're getting up there. The other alternative approach is event brokers. These are brokers that receive data, messages, queue them, label them, and they receive requests to access those queues. This is called publish subscribe or message-oriented middleware and things like that. There are a whole bunch of standards and technologies in that area. I once had the law of a millisecond, which says it always takes at least a millisecond to do that. So remember, that's much bigger than a microsecond, which is what MPI is. So when you start doing things sophisticated with and put a lot of software into the system, that software creates overheads, which are not networking overheads. These are software overheads due to the richness of the communication model. We note here HARP, which is from Indiana University, that uses the MPI technologies with the systems at layer 14 to get very good performance, especially with Hadoop. So if we come to the publish-subscribe systems, in the publish-subscribe system, data arrives somewhere, it goes in a queue which is labeled, the system it arrives at called a broker. It's distributed, so it scales and can take arbitrary number of messages. It labels these so-called topics, which is takes the topics, which are the things which labels the messages. It manages them. And they differ in the protocols, the API, how you access them, how rich you can put topic names, hierarchical, and wildcarding, and also the fault tolerance of the messages. Can they get lost? And what are the delivery guarantees? If message 1 is sent after message 2, is it delivered after message 2? So is message order guaranteed? So we have a wide variety of entries here. Kafka from LinkedIn is Apache. ActiveMQ and Cupid is also Apache. Of these, ActiveMQ is probably the best known, and they're pretty similar to RabbitMQ, which is a well-known open source product, and a system from Indiana University called the RADA Brokering, which at one time was state-of-the-art, but really hasn't been developed for the last 4 years. It's still, however, competitive in performance to ActiveMQ. Kestrel aims at simplicity, comes from Twitter, and Netty is built around Java and I/O and allows it to support protocols like UDP. ZeroMQ is a somewhat different model. It is not trying to buffer, it's actually trying to route messages between processes. And as well as these sort of open source methodologies, we also have the whole set of commercial capabilities from Amazon, Simple Notification Service, Google PubSub, Azure Queues, Azure Service Buses. These are all the equivalent technologies in public clouds. There's an interesting computing model called Lambda available from Amazon, which allows you to have events or any types of notification to start a compute instance. And Azure has things called event hubs, which are based on the service bus queues, which support the Azure Streaming Analytics, which is at layer 14B for the streaming. The various important standards. Java Message Service is sort of the very sort of old. It was introduced early on in Java. It was very important actually for bringing pubs up to mainstream. It's an API. It does not specify the message. AMQP is actually a protocol, so it specifies the nature of the messages. STOMP is another protocol, which is particularly simple and HTTP style. And MQTT comes from sort of the Internet of Things domain and could grow in importance because it's a way of, it's designed to do machine-to-machine communication, build intelligent machines and things like that. An area which is called the Industrial Internet of Things, which is of dramatic importance.